All right, so 3.1b, and for example 1, we've got a piecewise function. It's x squared plus x when x is less than or equal to 2, and it's 3x when x is bigger than 2. And for part A, the question is, does f prime of x exist at x equals 2? Does f prime of x exist at x equals 2? Okay, so with problems like this before, obviously we suspected that the function wasn't continuous at 2. So I think that's coming up later in the question, but I want to connect to what we're doing, what we've done before. Like if the question was, is it continuous at 2, what would you do? Yeah. Good. You take the limit as x approaches 2, right? And you also calculate f of 2, and then you see if they're the same. So that's what we've done before. We've taken the limit of f. That's if the question is it continuous? But this is a different question. This question is, does the derivative exist at 2? Okay, so if we want to figure out if the derivative exists at 2, we have to calculate the derivative at 2. Okay, and then the derivative at 2 is a limit, right? But it's not this limit. It's a different limit. Okay, so it's the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. So the derivative is the limit of the slope, right? Not the limit of just plain f, but the limit of the slopes. So the reason we're calculating this special limit called the derivative is because the question's talking about the derivative at 2. Okay, so we're going to just calculate this derivative and see what happens. All right, so the problem is we have two different formulas for f of x, right? So we don't know at this point which one to pick. If we were going to pick numbers less than 2, then this would be the formula we would pick for f of x. But if we were going to pick numbers bigger than 2, then this is the formula we would pick for f of x. So, and when you're taking the limit, you have to do both of those things, right? You pick numbers less than 2 and bigger than 2. So we have to split this up into two different limits. The limit from the right, and also the limit from the left. So whenever you calculate a limit, you do 1.9 and 1.99, and also 2.1 and 2.01, right? But in this case, we have to split it up because the f of x has two different formulas. So when we're coming from the right, that's going to be this formula for f of x. But when we come from the left, like 1.9, 1.99, that's this formula for f of x. Okay, now which formula do we pick when we're calculating f of 2? The top one, right? So that's going to come out to 6. Now, it's a coincidence that the bottom comes out to 6 as well. That may or may not happen, right? So when we calculate f of 2, we are using this formula. Both here and here, right? Because this right here is f of 2. Let me say that again. This right here is f of 2. And so when we calculate f of 2 for here, we're using this. And to emphasize that, because you'll forget that in your notes, I'm going to put this down. It's kind of weird that we're using one formula there and a different formula there. But it's all the same f of x, right? It's the same function. So of course that's 6, right? Okay, so when I calculate this limit, I can pull out a 3. Because that would be a 6, right? And then 3 times 2 is 6. And that's nice, because then the x minus 2's cancel. And the limit of 3 is 3. And then if you calculate this limit, you can factor it. So that's nice because the x minus 2's cancel, right? And the limit of x would be 2, and the limit of 3 would be 3. And so that comes out to 5. Okay, so overall, what is this limit that we're trying to calculate? Yeah, I heard some muttering. Just say it louder. Doesn't exist, right? Because we took the limit from one side and we got 3, and we took the limit from the other side and we got 5. And when you get two different limits from different sides, then the limit doesn't exist. So that means this limit does not exist. Now notice, this is not the limit of f of x, right? So that limit may exist. But this limit, that's the derivative, doesn't exist. This is the derivative at 2, and it doesn't exist. So that means f prime at 2 does not exist, because this is symbols for what we just calculated, right? And I guess the question was, does f prime exist at 2? So I guess the final answer is no, right? Yeah, Colin?
Looking at your work, shouldn't as limit of x approaches to the positive side, shouldn't that be using 3x in the piecewise function?
So I agree with you. When you plug in 2.1 into f of x, you'll be using the formula 3x. But when you plug 2 into f of x, you use the top formula.
So just like I know it didn't really like affect the answer, but like using for f of 2.
It doesn't matter. First of all, it does not matter that it didn't affect the answer. So your question is very valid, regardless of whether it affected the answer or not. This is just f, which could be either one of these. And for this f of x, we are picking numbers that are 2.1 and 2.01. And so that's why I chose 3x, because I know that x is bigger than 2. But here, this x is equal to 2. And so when I plug it into f, I have to use the top formula for f. You're getting to the center of the issue. Are you understanding completely or no? Okay, good. Thanks for asking. Is everybody else okay on why the answer is no on this? And Colin's exactly right. It's weird that we're using two different formulas there, but it's all one f of x. So f of x just happens to have two different formulas for it, but it's just one function. Okay. All right, so the answer was no. Now we're going to, for part B, we're going to find a formula for f prime of x. So we already know that f prime of x doesn't exist at 2, but now we also need to figure out what goes for f prime of x less than 2 and what happens for f prime of x bigger than 2. Okay, so for x is less than 2, we need to calculate the limit as x goes to a of f of x minus f of a all over x minus a. So it's asking us to find a formula for f of x. So that's why I'm leaving this as a, right? When you're trying to find a derivative for any number, you're not trying to find the derivative at a particular number, so you just leave that for a. If we were trying to find the derivative at 7, then we'd put 7's here. Or like in the part A, we were trying to find the derivative at 2, so that's why we put 2's here. But here, we're just trying to find the derivative at any number, so we're trying to find a formula, and so that's why we're leaving it as a. Okay, so when x is less than 2, f of x is going to be x squared plus x, right? And here, is a a number bigger than 2 or less than 2 or less than 2, right? It says right here. Now I'm trying to figure this out for numbers less than 2. So in this case, a is less than 2. And so I'm still going to use the formula x squared plus x. So that's going to be a squared minus a. Sorry, plus a. And then x minus a on the bottom. Okay, then we're going to calculate from there the limit as x goes to a. I'm going to distribute the negative, so that's x squared minus a squared. And then plus x minus a. So I distributed and regrouped, right? Okay, now I'm going to factor the x minus a squared. So that'll factor into x minus a times x plus a. Okay, now I can't divide this x minus a across a plus, but what I can do is I can distribute it. So what I mean is I can't just cross this out, but I can distribute across plus. So that's going to be x minus a times x plus a divided by x minus a plus x minus a divided by x minus a. So then here, these x minus a's can cancel. So that's x plus a. And these x minus a's come out to 1, because x minus a divided by x minus a is 1. Then I can do a bunch of limit laws. The limit of x is a, the limit of a is a, and the limit of 1 is 1. And so the formula that I get is 2a plus 1. Okay, so that means that for any number less than 2, if I want to figure out the derivative, I just have to take 2 times the number plus 1. So for example, for negative 5, the derivative would be 2 times negative 5 plus 1. And I keep using the word derivative, but what does that mean? What is the derivative? It's the slope of the curve, right? So if I want to know how steep this graph is at negative 5, I just plug a negative 5 into this formula. Okay, so I'm on my way towards figuring out the formula for f prime. For numbers less than 2, the formula is 2x plus 1. So that was what this formula told me. For any number less than 2, I just have to take 2 times the number and add 1 to get how steep the graph is. So this says the same thing, it's just using an x instead of an a. Just a represents any number, x represents any number, right? Okay, so now I got to figure out what's going on for numbers bigger than 2. Okay, so I'm going to calculate that over here. So I'm still going to calculate the same limit. But I'm going to calculate this for numbers bigger than 2. Okay, so I just erased my f of x, which probably wasn't the best. Oh yeah, thank you very much. Come on. Okay, we're good now. All right, so for numbers bigger than 2, what is f of x? 3x, right? So this time, I'm going to replace f of x with 3x. And if a is a number bigger than 2, then I'm going to take 3a for my f of a. And then this one's easier because the 3 just factors out, right? So the x minus a's cancel. And then the limit of 3 is 3. Does that surprise you that the slope is 3? For the straight line graph 3x, right? The graph for that part of it was just f of x equals 3x, right? So of course, if the graph is 3x, then no matter where you are in that graph, the slope is going to be 3. So for any bit number bigger than 2, this is just saying that the slope on that place is 3. Okay, so now we've got the rest of our formula. When x is bigger than 2, the slope is 3. Yes? So she's asking, what is the derivative at 2, right? She's wondering what goes on at 2. It's a valid question, right? Because I haven't mentioned that yet in this formula, right? What was the derivative at 2? We figured that out in part A, right? It didn't exist. So that's why I didn't want to put a line under here, because I would be saying that it did exist if I did that, right? So if I put a line under here, I'd be saying at 2, the derivative is 5. But the derivative isn't 5 at 2. The derivative doesn't exist at 2. And so we just don't even mention 2. And then after a while, you'll realize, oh, that means it doesn't exist at 2. Now, you could be over precise and say, okay, at x equals 2, it doesn't exist. But usually we don't write that line there. We just we decide, oh, if I don't mention it, then that means it doesn't exist. Good. Okay, so here's my formula for the derivative now, for this piecewise graph. Okay, so that was part B. And part C is f continuous at x equals 2? So with a piecewise graph, we often suspect that it's not continuous where the two functions cut off from each other, right? So when you saw f of x equals x squared plus x for bigger than 2 and 3x for less than 2, immediately you thought, okay, there might be a problem at 2. So that's why I'm saying, is it continuous at 2? Okay, but when you calculate whether it's continuous at 2, you just calculate the limit of f of x, right? Not the limit of f of x minus f of a all over x minus a. That's a different limit. They're both limits, but those are different limits. This is the limit of the y values, and over here, this was the limit of the slopes. Okay? If the question is about the derivative, then you want the limit of the slopes. But if the question's about asymptotes or continuous, then you want just the limit of the y values. Okay, and then also, to figure out if it's continuous, we need to know what f of 2 is, right? So to figure out if it's continuous, we calculate the limit towards 2, and we also calculate f of 2. And if those are the same thing, then that means it's continuous. So let's do this first, because it's easy. I think you use the top formula, right, for f of 2. So that comes out to 6. Again, it's a coincidence that the bottom formula comes out to 6 as well. On some, it might not. So make sure you're using the top formula when you calculate that 6. Okay, then for the limit, again, the problem is there's two different f of x's, right? So that means we need to split this limit into two parts. The limit from the right side. So this is called the right-hand limit. I'm not sure I've mentioned that during class before. I think the homework mentioned it one time. When you do 2 plus, that's called the right-hand limit because it's from the right side. And when you do 2 minus, that's called the left-hand limit. So we're splitting this up into the right-hand limit and the left-hand limit. If numbers were bigger than 2, like 2.1 and 2.01, then the f of x would be x squared plus x. But if, or did I mess that up? Is it the other way around? Because I erased my f of x, so. Is it 3x when it's bigger? Thanks for looking at me like I was crazy, Austin. So for numbers that are bigger than 2, it was the bottom formula. Yeah, so that was 3x. Everybody good? Okay, and then for 1.9 and 1.99, it's the number smaller than 2, so that's x squared plus x. And these limits are easier to calculate than the other ones we've been doing today. You just do limit laws, right? Limit of 3 and limit of x. You can just distribute past the times. So limit of 3 is 3, and limit of x is 2. So that limit comes out to 6. And this one you can do limit laws as well. Limit goes past plus and inside a square. So I moved it past the plus and also inside this square. And the limit of x is 2. And the limit of x is 2. And so this comes out to 6, right? So the left-handed limit came out to 6. And the right-handed limit came out to 6. So the overall limit is what? 6. Good. And so is the limit equaling the function value? Yes, it is. So does that mean that it's continuous? Yes, it does. So now we know that the answer is yes to this question, because the limit came out to the same as the function value. Okay, so that's kind of interesting. It's a continuous graph. That means it's connected. But it doesn't have a slope at the connection point. The derivative doesn't exist. That's what we found out in part B, right? Or part A. The question was, does the derivative exist at 2 in part A? And that answer was no. But then in part C, the question was, is it continuous? And that answer was yes. So so it's kind of interesting that the derivative can exist, but yet it be continuous, yet it be connected. That the derivative cannot exist, yet it's still connected. Okay. All right, now we're going to just digest the derivative formula a little bit more. Look at just 2 more examples. They're pretty quick ones. So the question here in example 2 is, what derivative do the following limits represent? What derivative do the following limits represent? Okay, so here's the first one. It's the limit as x goes to 7 of x squared plus 4 minus 53 all over x minus 7. Okay, so there's 2 different formulas for the derivative, right? There's the x approaches a method, which is the one I used today in part A. But there's also the h approaches 0 method, which I haven't used yet today. Which one does this look like? Does this look like h approaches 0, or does it look like x approaches a? Clearly x approaches a, right? Because there's an x there, and it's not going to 0. Okay, so this is a derivative, because it's a special limit. It's the derivative at what number? 7. Good. Okay, so a equals 7. So I'm just thinking backwards. I'm saying, okay, somebody apparently is calculating a derivative here, and I'm trying to figure out it's the derivative where and it's the derivative of what function. Okay, so there's the where. So now the next question is, what function is it that we're taking the derivative of? So what function is it that we're taking the derivative of? X squared plus 4, right? Because that goes right, f of x goes right there in the formula. And then you could just double check, like if this is a, that should be f of a, right? 7 squared is 49, and then 49 plus 4 is 53. So it's checking out. That is f of a. So we have f of x minus f of a all over x minus a. So what derivative do the following limits represent? Well, this derivative represents the slope of this curve at 7. So it represents the derivative of this f of x at x equals 7. So all you have to do to answer these questions is tell me what the a is and tell me what the function is. But what it means is, if we were going to calculate this limit, it would tell us how steep this curve is at 7. It would tell us the slope of this curve at 7, the final answer. Is everybody okay? So we've had problems where it said, okay, here's the function in the a, do this. Now we're just going backwards. I'm giving you this, and I want to know what the a is and what the function is, just so we get this formula down really solid in our head. Okay, here's another one. How about the limit as h approaches 0 of 3 plus h cubed minus 27 all over h. Okay, so I almost feel silly asking, but is this the h approaches 0 method or the x approaches a method? Clearly the h approaches 0 method, right? Okay, so we have to figure out two things. We have to figure out what a is. We have to figure out the number where we're calculating the derivative. And then we also have to we have to figure out what the f of x is, what the formula is that we're finding the slope of. Okay, so if you think you know either of these, raise your hand or tell me. Yeah, Annie? A is 3. How'd you know? Yeah, it's always f of a plus h here, right? So a is 3. Is everybody okay with that? This one's a little bit trickier than the x approaches a method. Okay, how about the f of x? Figured out a is 3. Yeah, Stephen? It's x cubed, that's correct. But just to double check, if that's true, this should be f of a, right? Is 3 cubed 27? Yeah, so that's checking out, because 3 times 3 times 3 is 27. So f of a is there. And then a plus h cubed is there. So there's our a value and our function. So if we finished calculating out this limit, which we're not going to, what it would get is, it would tell us how steep this graph is at 3. It would tell us the slope of this curve at 3. So that's what the h approaches 0 method does, and that's what the x approaches a method does. It calculates how steep a curve is at a number. Is everybody doing okay? Are you sure? Okay, that's all I have for today, so you can get started on tomorrow's homework.